All right, so here we're asked to do a proof by cases. Now, if you went into someone's office hours and asked how to do this problem, they'd probably glance at it and say, all right, line 1, line 2, let's just state our givens. P implies Q, not Q implies P, given. Then, well, let's look at line 2 and we can do the contrapositive. The contrapositive of line 2, well, since we have this hypothesis implies that conclusion, the contrapositive would be the negation of the conclusion, not P, implies the negation of the hypothesis, Q. Well, now look what we've got. We've got P implies Q, not P implies Q, and certainly either P or not P is true. That's just a tautology, P or not P. And then, by doing cases with lines 1, 3, and 4, P gets us to Q, not P gets us to Q. We have one or the other. Proof by cases says, therefore, Q. And this is a pretty straightforward proof, but if you're not familiar with how proof by cases works, it might not be immediately obvious why we did what we did. So I'd like to actually do the problem again. Now, we are suggested do a proof by cases using P or not P. What that means is we want this to show up. And I'm not necessarily sure how yet, but these are going to be our two cases. The two cases are P or not P. Our desired conclusion is Q. So what we need now are we need two different conditional statements. We need P implies Q. So I don't know how I'm going to get that, but I'll call it line 2. And what we also need, if this hypothesis gets us to Q, we also need this one to get us to Q. So having established our cases are P or not P, if P gets us to Q and also not P gets us to Q, then at the very, very end, we can simply say we must have Q. So I don't actually know what my justification is yet, but if we have lines 1, 2, and 3, then we can simply do a proof by cases combining them, and we would say we either have P or not P, P gets us to Q, not P gets us to Q, so we'll get to Q one way or the other. But now we come back and ask, what are the justifications for these lines? Well, line 1, that's just a tautology, so we can introduce it for free. Line 2, P implies Q, oh, that's actually a given, so that's totally allowed. What about not P implies Q? If I don't know where it came from, I have to make it an assertion. But an assertion has to be followed up by an assumption. Well, I asserted a conditional statement, so maybe we're going to do a direct proof of this conditional statement. So I'm going to assume the hypothesis of what I asserted, which is not P. If I can ever make the line Q show up, well then, that would complete the proof of this assertion. So I don't yet know how I'm going to get from this hypothesis to this conclusion, but we've got the structure there. We introduced a tautology, we stated a given. We made an assertion, you always can, however it has to be backed up. So before we can actually get to the end, we do need to finish up this proof. But we're going to try a direct proof, so we assumed not P, and I just need to make Q show up somehow. And I've left blank space because I don't know how long it's going to take. And your mileage may vary with different instructors, but for me, this is worth a lot of partial credit. If you just presented this, of course the problem isn't done, but your presentations of line 1, 2, 3, 4 tell me that you know how proof by cases works. Line 3 being an assertion says you know that you don't just get it for free. Okay, not P implies Q wasn't one of your givens, so you don't know where it's coming from, so you assert it. And you recognized that it was a conditional statement, so you're going to do a direct proof, and you're going to assume the hypothesis and work towards the conclusion. The empty space here tells me you recognize you don't know how you're going to get there, but you know that's the goal, to move from not P to Q. Once that's done, that box will then justify line 3. So let's go ahead and fill this in. So we've got not P, and you ask, how does that go with what you've already got? Well, not P doesn't combine with this, Okay, and you could do an elimination technically, since you don't have this, you must have that, but that would just be a duplication of what you already have, so you don't get anything there. And the negation of the hypothesis gets you nothing in a conditional statement, so nothing there, but we do have another given, so let's go ahead and state it. So for line 3.2, we'll throw in the other given of not Q implies P. It's a little unusual to see this show up here rather than right at the beginning. Typically, a lot of students will just throw out the givens at the beginning to get them into the proof, and that's fine. Okay, but we started with how does a proof by cases work, and now we're seeing that we do need that given after all. So with not Q implies P and not P, we can just jump right here and do a modus tollens between lines 3.1 and 3.2. Okay, so with the negation of this conclusion, we get out the negation of the hypothesis. Now this box is complete, the assertion is justified, and the proof is done. So this is another way that we could do the same proof. The benefit here is that it more directly starts with how does proof by cases work. The previous proof is totally correct, don't get me wrong, but if you've never done proof by cases, it might not be obvious why the steps were done in the order they were done. So let's take a look at another one. So I'm going to do the same sort of style we did in the previous problem. We are asked to do a proof by cases, P or not P. So we're going to need the statement P or not P. Now we recognize that now as a tautology. I'm going to go ahead and throw that justification in there. Our desired conclusion is Q. So from P, we need to get Q. From not P, we need to get Q. So for line 2, I'll say P implies Q. And for line 3, I'll say not P implies Q. Then, if those are complete, we can just do a proof by cases of lines 1, 2, and 3, and we'll get out Q. P or not P. P gets me to Q, not P gets me to Q. Either way, we get out Q. However, we need to somehow justify lines 2 and 3. They're both just assertions at this point. And assertions have to be followed by assumptions. Both of these are conditional statements, so we'll try a direct proof. Okay, we assume the hypothesis P, we assume the hypothesis not P. In both cases, the conclusion we're working towards is Q. If we can get from P to Q, we can box all of this off and justify the assertion in line 2. If we can get from this not P to that Q, we can box all of this off and justify the assertion in line 3. If lines 2 and 3 are justified, then the proof by cases will be complete. So now we ask, all right, how do we get from one place to another? Well, if I have P as a valid line, maybe I can combine it with this given. Indeed. So we've got P, which means we don't have this, but we either have not P or Q, so a straightforward elimination between lines 2.1 and 2.2 gets me Q. Now we have gone from P to Q. That justifies the assertion in line 2. One thing that's worth pointing out is inside this box now, I cannot refer to these lines. I cannot refer to lines 2.1, 2.2, or 2.3 anymore. They were all in service of the assumption in line 2.1. This is an assumption, but I don't actually know that P is true. That's not one of my givens. It's part of the format of the direct proof, but now that that direct proof is done, these lines are off limits. However, line 2 has now been proved, so line 2 can be referred to, which is good because I want to do it at the end. So for line 3, it's still an assertion. We don't know it yet, but let's see what we get. We made the assumption of not P. But look, we have this given. Not P implies Q or S. That's a given. I can state it here, and now I can apply modus ponens between lines 3.1 and 3.2 to get out Q or S. But I also have this given, S implies P. Now I can apply modus tollens between the assumption in line 3.1 and the other given that we just stated in line 3.4. If I don't have this conclusion, then I must not have had this hypothesis, so we get out not S. And now that we have not S, but we did already state either Q or S, a nice straightforward elimination between lines 3.3 and 3.5 tells me, as line 3.6, that we must have Q. So from the assumption of not P, combining it with these two givens, we got Q or S, but we also got not S. We eliminate this disjunction to get out Q. So not P logically leads to Q. Therefore, this assertion has been justified. Now that lines 2 and 3 have both been justified, I can refer to them along with the tautology in line 1 to do a proof by cases and extract Q. Not the only way you can go about this problem, but I like to start with the proof by cases structure and then start justifying the steps from there. Next up, proof by cases, but we're not told what cases to use. So we know we want to get out R. If we want to get out R, what we need is two different conditional statements that point to R. We don't have any givens that are conditional statements that lead to R. However, this almost is. So for line 1, I'm going to state the given of not R implies P. That was a given. And the contrapositive of it would be that not P implies R. And now we sort of see a proof by cases suggested. Not P gets us to R. We already have that and it's justified. If we also had that P implies R, then I could, at the very, very end, simply state the tautology P or not P, and then I would have a proof by cases. P gets me to R, not P gets me to R. I have either P or not P, therefore I conclude R. And that would be a proof by cases. Let's look at some line numbering. Line 3, I don't know why that's true, so I can't use it yet. It's an assertion. But observe that if I manage to somehow justify this assertion, that's actually all I need to complete the proof. So if line 3 is justified, I would jump right to line 4, and this would be line 5. Then the proof by cases would just be between lines 2, 3, and 4. So what I'm getting at here is, this is an assertion. I don't know that it's true. I need some sort of sub-proof to justify this assertion. But once that's done, line 2 is justified, line 3 is justified, I would move on to line 4, which would be my tautology P or not P. Now, assuming we've completed all of this and line 3 is legal to refer to, between line 2, 3, and 4, not P gets R, either P or not P, therefore R. So now let's look at how to justify the assertion in line 3. Well, assertions are followed by assumptions. We asserted a conditional statement, so let's go ahead and try direct proof. So we're going to assume P, and we're going to need to work towards R. Now you might ask, if I can make R show up, why on earth do I need to do it down here? Well, because this will be part of the proof of the statement P implies R. Once it's boxed off, you can't refer to it anymore. In other words, this R isn't existing on its own. It's subservient to this assumption, and you don't really know that P is true. So that's why this R does not conclude the proof of this one. The combination, however, that P gets you to R, not P gets you to R, and either P or not P, that does get you R on its own. So continuing with the proof of line 3. We just assumed P, and we've got some givens we haven't used. For example, P does imply Q. That's a given. So now I can do modus ponens between lines 3.1 and 3.2 to get out Q as line 3.3. Oh, but look at line 3.4. Q implies S, that's a given. Now I can apply modus ponens between lines 3.3 and 3.4 and extract S. I'm not necessarily sure where this is going. I'm just sort of doing what I can. One way I like to phrase this in class is first ask if you can do it, then argue or worry about whether it's useful. But I can do all of these steps, and I hope they're useful. We've got an S. Well, heck, for line 3.6, let's introduce S implies not P. That's another given that we haven't done. Then I can do modus ponens again between 3.5 and 3.6 to extract not P. At this point, students may be concerned because we have P, we have not P. That's a contradiction, isn't it? Yes. That doesn't matter. We're not doing an indirect proof, so getting a contradiction isn't the end goal, but just constructing one as part of a direct proof is not necessarily a problem. Okay, because we're actually just going to use this not P in combination with the original given. Actually, we did a contrapositive already in line 2. Line 2 is already justified, so we can refer to it. So we can do a modus ponens between lines 2 and 3.7, and that's just going to get us, since I have a not P, and we have a fully justified line that not P implies R, we get out R. And that's all we needed to conclude this box off. So this is a little unusual in that we had a P and we had a not P, which is a contradiction if you were to conjoin them together, but we weren't doing an indirect proof, so that's not actually really relevant. We just needed to get from P to R. We happened to do an intermediate step where P must imply not P. And yes, that's a contradiction, but all we needed was the not P to do a modus ponens with our earlier justified line that not P implies R. Okay, another proof by cases. Well, we want to get out Q. That's the desired conclusion overall, and we actually have a conditional statement P implies Q that is one of our givens. So that is a pretty big suggestion that I want to introduce P implies Q, that's a given. We'll use the tautology P or not P. Then the other conditional statement that's missing is that not P implies Q. I don't know why that would be the case, so I'm just going to assert it. However, if we can back this up, sorry, not P implies Q, just wrote that incorrectly. So this given, this tautology, P gets me to Q. If we can justify that not P also gets us to Q, then at the very end, as line 4, we can just say by cases between lines 1, 2, and 3, we must have Q. However, this assertion has to be justified, and I don't know in advance how long it's going to take. I hope it's not going to take this many lines. Probably won't. But let's go ahead and box that off. Assertions are followed by assumptions. We asserted a conditional statement, so we could do a direct proof. Just to change things up, maybe I want to try an indirect proof. In which case, I'm going to assume the negation of everything I just asserted. Okay, now I'm doing it in kind of a needlessly long way, but whatever. I have a negated conditional statement, so that would be hypothesis and negated conclusion. So that's a conditional equivalence on line 1. 3.1, sorry. I've got an and, so let's go ahead and specialize those. Not P, not Q, those are both specialization of line 3.2. All right. What can we do here? What can we do? Well, we are trying to get out any kind of contradiction we can. And lo and behold, we've got another given that we haven't used, 2 other givens we haven't used. So let's throw those into the mix. They're probably going to be useful. So we have S implies P or Q. And we also have S, those are givens. I'm allowed to state them now. You're always allowed to state your givens. Well, those actually feed together very nicely. With a modus ponens, I can immediately combine those 2 givens and simply get out P or Q. And now observe, we have different eliminations we can do. P or Q, not P, would give me Q. P or Q, not Q, would give me P. Either one of those is totally valid. Let's just go with the first one. So P or Q, not P, therefore Q. So that was an elimination. between lines 3.7 and 3.3. That gives me Q. But look what we have now. We have Q and we have not Q. So I'm simply conjoining 3.4 and 3.8. We already had the not Q floating around. We now got a Q. If we had done the other elimination, not Q combines with this to give us a P, which I could conjoin with not P. And either way, we're going to end up with a contradiction of something and its negation. So we were doing an indirect proof. We made the correct assumption, flatly negating the entire statement and then seeing what happened. We got a contradiction. So this line can't be true, which means this must be. So line 3 has now been justified. So it can be referred to in line 4, which concludes the overall proof of Q. And again, this Q does not conclude the proof overall, because this Q was all subservient to the assumption in line 3.1, which was just part of justifying line 3. Once line 3 is justified, however, proof by cases can be used and get out the Q that we need. All right, moving on to some quantified statements and predicate logic. Okay, so we have 3 people, Agnes, Bert, and Carla, referred to as A, B, and C, respectively. We have predicates for whether a person is happy, thirsty, whether one person loves another, is shorter than another, or is taller than another. And we're just asked to translate into predicate logic statements. So for the first one, Bert is happy. Now, Bert is referred to with the letter B, and a person being happy is referred to as H of that person. So Bert being happy would be this. H of X means X is happy. B is Bert, so H of B means Bert is happy. For 2, Carla is shorter than Agnes. Well, X is shorter than Y is S of XY. So what we want is S of 2 people. And observe that the first one is shorter than the second one. X is shorter than Y. So Carla is shorter than Agnes. So Carla is shorter than Agnes. Next, we have one person loving another and another person loving a third. So we have one person loving another and another statement about 2 people and their loving relationship in one direction. So Agnes loves Carla, X loves Y is L of XY. So Agnes loves Carla and Carla loves Bert. There we have it. For line 4, we have a conditional statement. So we have a hypothesis is going to imply a conclusion. If Bert loves Carla, so this is something to do with a love statement, and then a negation of a happy statement. Well, if Bert loves Carla, then it is not the case that Agnes is happy. Okay, we have some redundant parentheses here, but that's not necessarily a problem. Finally, if Bert is happy, then Bert is not thirsty. So again, we have a conditional statement. The hypothesis is that the happy statement applies to Bert. If Bert is happy, then it is not the case that Bert is thirsty. So if Bert is happy, then it is not the case that Bert is thirsty. Bert is not thirsty. Working with the same Agnes, Bert, Carla, happy, thirsty, loving, short or taller, etc., we have some more complicated statements. Now, I'm actually not in the habit of assigning a lot of problems like this because written language can be very vague compared to predicate logic, and we'll see what I mean there. If anybody loves Carla, then Carla is happy. Nobody is taller than Agnes. This is 2 different statements. So if then, the conclusion is that Carla is happy. Then Carla is happy. If anybody loves Carla, well, anybody is an unknown. It's a variable. So if X loves Carla, then Carla is happy. And what does this refer to? Any single person. If there exists an X so that that person loves Carla, then Carla is happy. Now, parentheses are actually quite important. The correct phrasing here is this. If I had placed parentheses, there exists in X such that, and then I put parentheses all around like this, that would say there is a person so that if that person loves Carla, then Carla is happy. In other words, there's one single person so that if they love Carla, then Carla is happy. But that's not what this says. This didn't say there is a person so that if that person loves Carla, Carla is happy. Carla will take anybody's love. If anybody loves Carla, then Carla is happy. If there is a person that loves Carla, then Carla is happy. Okay, the second part here, nobody is taller than Agnes. So it is not the case that there is a person so that that person is taller than Agnes. So X is taller than Agnes. There is not such a person. There is not a person that is taller than Agnes. The second one, if any person loves themselves, then that person is happy. Here we're going to see one bit of language ambiguity. Okay. So if any person loves themselves, then that person is happy. So if the person loves themselves, so if X loves X, then X is happy. Who does this apply to? Everybody. And again, parentheses are important. If the parentheses only applied here, it would be if everybody loves themselves, then X is happy, but X would be unquantified. We'd have a problem. Why here did anybody become existential, and here any person was universal? Well, really this means for every person it is the case that if that person loves themselves, then that person is happy. But if we had written, if every person loves themselves, then that person is happy, it would mean the same thing, but it sounds a little weird to my ear. Spoken language is just ambiguous when it comes to logical statements. But I think the reasonable interpretation here is that for every person, if they love themselves, then they are happy. If this was existential, that would just say there is one person that if they love themselves, they are happy. But we're saying any person loves themselves, then they're happy. Okay, for the third one, if any person is thirsty, so if there exists a person that is thirsty, then either one thing or another, either there is a person that loves Carla, or it is not the case that there exists a person that is taller than Agnes. What does this mean? I don't know, it doesn't really matter. But logically, that's what we've got. Okay. If there is a person that is thirsty, then either there is someone that loves Carla, or there is not somebody that is taller than Agnes. Nobody is taller than Agnes. Fourth one. If any person is taller than another, then the second person is shorter than the first. So for every person, for every second person, if X is taller than Y, then the second person is shorter than the first. Okay, this set of parentheses is actually not typically written. We would simply say for any X for any Y, or even just for any X comma Y. If X is taller than Y, then Y is shorter than X. However, it is not true, so as the sort of second statement here, we would say it is not the case. It is not the case that if a person is not taller than another, so it is not the case that for any X for any Y, if X is not taller than Y, then the second person is taller than X. I need a third one. There we go. So it is not the case that for any two people, if the first is not taller than the second, then the second is taller than the first. Okay, thinking of these heights as numbers, This is saying if x's height is bigger than y's height, then y's height is smaller than x's height. But it's not true that if x fails to be larger than y, then y must be larger than x, because the two numbers could be equal. That's essentially what this statement here is saying. Okay, but logically, this means what it says, but it can be fairly difficult to interpret a written statement as its sort of logical counterpart. Okay, and this is a big problem. A lot of people speak things that if you interpret them literally what they said, it's not what they meant. Okay, the classic example I give is a lot of people like to say, suppose a group of people is trying to decide where to go to dinner, and one person suggests, let's go get pizza, and a second person is tired of this first person always suggesting pizza, and they say something like, everybody doesn't want pizza. What they meant was, not everybody wants pizza. What they said was, everybody doesn't want pizza, but that's actually manifestly false. Someone did suggest it. Anyway, part 5. If Bert is happy, then there is a person who loves everybody, and there is a person whom everybody loves. So, if Bert is happy, so way at the beginning we can say, if Bert is happy, that's not quantified, it's about Bert, then there exists a person who loves everybody, so that given every y, x loves y. And there is a person whom everybody loves. So let's look at this. If Bert is happy, then some stuff happens. There is a person, there is an x, who loves everybody. So for every person y, x loves y. And there is a person, and there exists an x, whom everybody loves. So every person, y, loves x. Notice that this x is not necessarily the same as this x. There is a person so that for every y, x loves y. And there is a person so that for every y, y loves x. But there's no implication that these are the same person. This x is bound to this existential modifier, quantifier, and this x is bound to this one. They are not necessarily the same x. Anyway, that's it for this assignment.